Hello everyone, welcome back to LeetCode Daily Life where I do the daily question raw and uncut. So we have a medium called maximum Manhattan distance after k changes. So you're given a string s consisting of the characters, N, S, E, W, which I think are the directions, right? So where SI indicates movement in an infinite grid. So yeah, N is move up, it's like move north, so like move up. South you move down, east you move to the right, west you move to the left by 1 unit for each of them. So initially you're at the origin, 0, 0. You can change at most k characters to any of the 4 directions. Find the maximum Manhattan distance from the origin that can be achieved at any time. Oh, it could be any time, okay. While performing the movements in order, a Manhattan distance between two cells is so xi minus xj and iy minus yj. Maybe I can like draw out the Manhattan distance a bit to like make more sense. But let's look at the bounds first. Yeah, okay. So we have 100,000. We have 100,000 words. Wait. 100,000 like directions, and k is like, also 100,000 ish. Well, yeah, it will be 100,000 at most, and like our string only has the 4 directions. So, let's look at some example first. But before that, maybe I can draw out what Manhattan distance means. So if you're on a grid, Manhattan distance. So like normally you calculate the distance like if I can draw. Yeah, normally you calculate distance like this, right? But Manhattan distance you calculate based on the 2 components. So you have the x components plus the y components. And Manhattan distance would be just x plus y. So you don't have to do like the x squared plus y squared divided by like square root thingy for the actual distance. Like you just like add these together. Okay. So example 1, so you just have this thing here. The output is 3. So let's see why. So we can change one of the directions, right? So you change S2 from S to N. The string S becomes NWNE. So if we look at this, yeah, okay. So I think like for these questions, I should probably draw it out, so it makes more sense. So basically, before before any of the changes, the path will look like this, right? So it will be northwest, southeast. But if we change our third operation into a north, so I think we can, yeah, we can change it to any direction, right? So we can just change it into something like favorable for us. And also we want to know the maximum distance from the origin that can be achieved at any time. So it doesn't have to be the endpoint. So if we just like change, the south. So if we change the third operation into either north or west, well, the Manhattan distance here will be 3, right? And because we only change one thing, like the movement afterwards, we bring it back to 2. But like the maximum we can get to is 3 here. Right, so that's the first thing. Let's look at example 2. So example 2, we have we can actually change 3 of them. So let's draw up another grid. So we have north south, west west, So yeah, north, south, west, west, east, and then west. So it will end at this point here, right? Or like for the original path, but we are allowed to change three of them. So the answer is suggesting to change the first one into a north. So if we're changing it into a north, well, it would just be let me use blue here. So we change that into a north, and then if we follow the new path now, we will change east into west. We change east into west, and it actually only uses two operations out of the three that are available in this case. And in this case, we will get well, we will get well, let me count. So 1, 2, 3, 4, 5, 6 from the origin, like for Manhattan's distance. So that's why we have 6 here. Yeah, okay, so I understand the question now. I hope you guys do as well with my drawing here. My initial thought for this question is that we have to try all 4 directions. So our maximum could either lie around it could either lie around like this quadrant. It could lie around this quadrant and this one and that one, right? And like for the quadrants, we will also count the x and y axis. So like for example, this could be in this region or it could be in that region. Yeah. So if we have our maximums in either of these 4 quadrants, well, that means we want to move it there. Like we want to move from this direction as far as possible. So let's say we are focusing on like the first quadrant, right? We want to move our path like as far up and as far right as possible. Well, I think what we can do is we can actually just greedily change any of the directions that does not move that way. And we want to change the ones at the like as early as possible as well. Because so let's say we can think about this in like the 1D situation, right? So if you have like north, like right, left, yeah, something like this, right? I think like it'll be better if you change the one earlier first, because then like you can reach like because we don't have to like it will end at the same position if we like change this as well, right? But then yeah, but then like it just makes it more optimal in some sense. Like if you think about the intermediate distances, so we will have like so if we change the last like left, we'll have like 1 2 1 1 2 1 yeah, and then like 2 3 4, right? Wait, is that even true? Let me redraw that. So my idea, oh yeah, originally it looks like this, right? So if we change the first one, so if we change this to a right, it will be 1 2 3 4 3. If we change this one, it will be 1 2 1 2 3. If you look at each of the intermediate changes, well, yes, at the end it's the same. Here is the same. It's the same here. But if we look at these ones, changing the earlier ones actually gives you a better intermediate distance. but like we are also interested in all the intermediate distances, right? Like because uh like we are trying to find the maximum distance that we can achieve at any time. So that's why we will change at as early as possible. But we also have to check for all four quadrants because like our maximum could lie on either of these four quadrants, right? So so for example, for the first quadrant, you want to move whenever you see a south, so a south goes down, you want to go up and right, right? Whenever you see a south, you want to change it to a north. Whenever we see an east, which is whenever you see a west, which is going to the left, we want to change it into an east, right? So we want to change that like as much as possible, and then see how far we can go from that point on. And we have to like do that for every direction. And I think that would exhaust all the different cases, and it should work. So yeah, let's code this out. So we have the four directions. First of all, we can have a direction map. So north represents going up once. Yeah, and then so here I'm using the math coordinates instead. I think like I always get confused with the the computer science and the math directions, because like computer science usually like have up as like the first element. Like if you think about it, like if you go up, it's like going up one road, right? But like in math, you have like the x-axis and the y-axis. So I'll use that here. So here it will be -1 and 0 for west because we are going left, and then south we are going down. And then what else do we need? Yeah, I think we just need like the four directions now. So we should have like I don't know, like best x, best y. Do we need we can just have like the max dist here, and then we have our current x and y distances that we can reuse, right? I guess we can like just put it down here. Can we do it in loop, or do we just do it in 4 blocks? Let's just do it in 4 blocks. I think that's a bit easier to logic with. So we have the first quadrant, which is north and east. So first quadrant is this one. We like north and we like east. So so we have like initially we have this, and then now for I guess we should also have like operations. So like when we reach k operations, we can't change anymore, right? So for I in range, let's also have n as length s there. So I in range n. So I want to look at each operation. I guess we don't need that at all. We just we can just do like for character in s. So now, so if character in I guess like what we can do first is we can just check if character is north and east first. So north and east. Well, if the character is north and east, we can just update our xy coordinate, right? Cause like that's good for us. So I'm not sure if we can like just wait, a tuple is like not updatable, so we need like dx dy. It will be a direction map of c, and then we'll do we'll add that, and then add that to our y, and like we move that further, right? Otherwise, so if it is like one of the directions that we don't like, so if operation is if it is larger or equal to k, I guess like we just want to do the same thing. I can probably like put it up here. So yeah, if operations are greater than k, so like this is like when you know that c is like the direction is no longer favorable, but we can't change any more stuff. Like we just want to update like that, right? But otherwise, if the direction, if yeah, but otherwise, so that would be like if the direction is south and west, and we still have some operations there, so we need to like add one to our operation. I guess we can like do it here as well. So so dx dy, we also don't really need the opposite, because like in the first quadrant, whenever we see an unfavorable movement, we can actually move either north or east. Like we can change it to either north or east, because like both of them increases the distance by 1. So it doesn't really matter in that sense. Yeah. So what do we want to look at now? I think, yeah, okay, so we can just change, we can just do like, you can just add 1 to x, I guess. Like that'll represent our, like that represents a change like into the east direction, right? So I can do that, and then yeah, and then but every time we also have to check whether we have a better max distance. So we have to do a running max, and then x plus y. So I think that's all we need to do for the first quadrant. And then we can just copy these and like make sure we change everything correctly. That's definitely one of the biggest challenges of this question, is like to write correct code. Okay, so second quadrant. So second quadrant will be this quadrant. So in this quadrant, we want north and west, right? So we have north and then west. And again, we set x, y back to 0, 0. Set operations back to 0. So if it is in north or west, we'll just do that. Otherwise, we actually want to move west this time. Or, well, we can move north, but either way works, I'm pretty sure. So, yeah, so let's just do that. And, yeah, is the rest the same? Let's see. Yes, I think the rest of the stuff are the same. Yeah, so we have third quadrant here. So that will be this quadrant. So south and west. So we have south, west. And yeah, again we can move west here. So we just do x minus 1. And then for the fourth quadrant, we will have east and south. So you can just change that, and yeah, we can move east. So at the end, we just want to return max distance. Well, like if you want to combine the operations together, you can like you can just make a list for this thing here, and like for this here as well. All right, we got 2 here for some reason. So I think for this case, we can actually move like northwest, northeast, right? So in that case, wait, northwest, north. So which one is northwest? So let's look at the second quadrant. Wait, actually, what will happen with the first quadrant? So first quadrant it will do northeast and then southeast. So yeah, actually that one wouldn't get as far. So I think we should have a max distance of 2 there. What about here though? Yeah, I think this is the one where like we should make sure is correct. So we can just print x and y here. Let's see what's going on. So yeah, okay, so we start with like 0, 1. We move to I forgot the absolute values for these distances. That's my bad. Yeah, so let's just do that. So the reason we need absolute value is like we care about the distance, not like the direction of it, right? So if it is -1, we still count that as 1. So let's just fix that quickly. And I hope we get the correct answer now. Okay, that looks good. Let me mute my print statement here. The acceptance rate is very low, so I won't be surprised if I run into edge cases. Oh, okay, we did not run into any edge cases, so that's really good. And yeah, I guess I can talk a bit about how I thought of the solution. But actually, like, I think this question is like one of the questions where like at first glance you can like kind of already see how it is done. But yeah, I also like made some explanation before, but I'll just reiterate them here, in case like you're just looking for like a solution at the end. So yeah, well the first thing is I hope this makes sense, like why I split it into 4 quadrants, like when I'm checking. Well, because like it is possible that you have a path that let me draw another grid. That grid is like pretty messy right now. You can have a path that goes like something like this, right? Which like crosses the different quadrants. But we want like if we want the maximum, we have to be very decisive onto which directions we want to move to the most. So if we want to move to the first quadrant, we want to move as upward as possible and as right as possible, right? So we don't want to mix any like lefts in unless unless we don't have any operations left. But like in that case, like in this kind of case, actually like it would be better if you like if you move to the left instead, like you get a better answer here, right? Yeah, but if we are focusing on like some directions, so like for example for the 4th quadrant, like you want to move right and down, right? So if we have that in mind, how do we achieve that? Well, this for this we have to go back to like our greedy approach here, which if you think about the 2D grid and separate it into going vertical and going horizontal, it could be something like this, right? So you could be like moving right 2 times, moving left 1 time, moving right 1 time, and then moving left another time. If we change the first, well, we want to move as right as possible, right? So if we change the first left, we will get these like these like distances, like calculating like how far right it has gone. If we change the left one, we will get this one. Well, yes, like when we just change one of them and switch it to right, we will have the same ending, running distances. But the question is interested in the maximum Manhattan distance that can be achieved at any time. So it could be like this time as well. It could be this time as well. And like clearly you can see that if we change it earlier, we actually get a 4 here. And well, why is that? Well, because like if you think about it, if we change the early ones, we will be moving far right, um, like as early as possible. So like we will be going like this direction more, and then like we'll kind of rebound. But if you change like some like if you keep some left in the middle, so something like this, um, like eventually you reach the same thing, right? But you wouldn't have rebounded as much to the right as possible. So I hope that kind of makes sense. And like if you apply the same thing for vertical as well, like the thing to see is like like if you greedily change like the first occurrences of the opposite direction for both horizontal and vertical, well, your running distance will always be better than like if you don't do that. So if you do that for both vertical and horizontal, you rebound you basically like stretch to as far as possible before you kind of like rebound back at the end. So like we're interested in this point, right? And like yeah, I hope my explanation kind of makes sense. But like you can think about it as like a rubber or something. Like you want as much momentum as possible at the beginning, get that point, and then like let it rebound back. So yeah, I think this question is pretty interesting. I can see a lot of potential pitfalls for this question as well, but I kind of got a bit lucky and I got this first try. So yeah, if you have any questions, please leave it below, and please leave a like if I help you out in some way. That will help the channel a lot. So yeah, thanks for watching, and I'll see you tomorrow. Bye.